In this video, I'm going to introduce you to the product of inertia, which is IXY. IXY at first appears fairly simple, but it really has some interesting features, some interesting properties. And so we're going to take some time talking about product of inertia, why it's used, where it comes from, kinds of problems that we're going to work. And so we're going to spend some time on product of inertia. It's a complex animal. Let's just put it that way. And so I'll try to help you appreciate what it is and what some of its properties are. And again, in this video is just to introduce you to the scope of IXY. And then successive videos will go into details of the pieces. So product of inertia is IXY, or sometimes we just call it POI, for product of inertia. We've already talked about moments of inertia, IX and IY. They're properties of areas, where IX is the integral over the area of y squared dA, and IY is the integral over the area of x squared dA. I pointed out to you that you have to be careful with these definitions. These are true for double integrals, and they're true for properly chosen dAs. For example, a dA that's parallel to the x-axis for IX, and then a dA that's parallel to the y-axis for IY. If you do those correctly, then the integrals are simple. Product of inertia is defined as the integral over the area of xy dA. And so again, it's the same area, it's the same dA, it's xy. And this is the way Hibbeler gives it on his crib sheet. But this definition, as listed, is really only true for a double integral. If you use a single integral, it's a little bit more complicated. Now you've got more choices of dAs than we did for IX or IY, which we'll get to more in the details when we do a product of inertia by integration. For example, again, integral of xy dA is strictly true only for a double integral. Only for a double integral is x the distance from the y-axis to the centroid of dA, and y is the distance from the x-axis to the centroid of the dA. For product of inertia, let's say you decide to use a horizontal element, which you can do. Well, if you use a horizontal element, then the distance from the x-axis up to there is y. But the distance from the y-axis to the centroid of this dA is x tilde, which is the distance to the centroid of the dA. And so x tilde is the average of x left and x right. So x left plus x right over 2. So strictly speaking, it's like an x tilde times a y dA if you use a horizontal element. If you choose to use a vertical element, then the distance from the y-axis to the centroid of this element is x, but the distance from the x-axis up to the centroid of this guy is a y tilde, which is like the average of y bottom plus y top divided by 2. So strictly speaking, it would be an x times a y tilde dA. So nobody ever writes them this way, but I'm trying to help you appreciate the nuances of this definition and what it is and what it isn't, and what it implies and what it doesn't imply. We'll say more about this when we get to integration, but just keep that in mind. But this is the generic definition. IXY is an integral over the area of xy dA. Why do we want product of inertia? Where did this come from? Well, shortly in a different video, we're going to derive transformation equations, where if you're given IX, IY, and IXY for a given area at a standard XY coordinate system, we're going to be interested in calculating I, X prime, I, Y prime, and an I, x prime, y prime, for a set of axes that are rotated some angle theta from our original coordinate system. When we derive those transformation equations, one of the terms that appears in that derivation is an IXY term. And so IXY then becomes part of the process of calculating those rotated axes. So in other words, to calculate I at rotated axes, or to calculate I min and I max for a given area, you need all three. You need IX, you need IY, and you need IXY in order to get the rotated values and in order to get the principal values. In other words, the I max and the I min. So we need it. We need IXY. So remember, for IX and IY, moments of inertia, for any given area, they are always positive and cannot be zero. And that's because of the x squared and y squared terms. So IX is y squared dA. So whether y is positive, whether y is negative, you're squaring it. And the area is always positive, and so IX is always positive. And IY is the integral of x squared dA, and x can be positive or negative, but when you square it, the result is always positive. However, IXY, product of inertia, can be zero, positive, or negative. And it's because of the XY term. We're not squaring them. We're taking an X value times a Y value times a dA. So it's a result of the definition. For a shape with an X or Y axis of symmetry, where in other words, half the area is on one side of the axis and half is on the other, when you add up all the X's and Y's, they cancel one another out. Although the positive XDAs cancel out the negative XDAs, or the positive YDAs cancel out the negative YDAs. And so for all of these symmetric shapes about a set of centroidal axes, all of these have a product of inertia of zero, which simplifies some of our calculations. For example, our product of inertia calculations for IXY. For areas in different quadrants, the X and Y terms can each be positive or negative. For example, if you have an area in quadrant 1 and a given dA, you've got a positive Y, a positive X, and when you take the XY product, the result is a positive IXY for an area that lies in quadrant 1. For an area that lies in quadrant 2, and you integrate that guy, the X terms are negative, the Y terms are positive, and so the product of negative X times positive Y gives you a negative IXY for an area that lies in this quadrant. For an area that lies in quadrant 3, the X's are negative, the Y's are negative, so the product of negative X times negative Y is a positive IXY. And finally, for an area that lies in quadrant 4, the X's are positive, the Y's are negative, and so the product of positive X and negative Y gives you a negative IXY. We'll say more about this later, but for a general area, if a general area lies in quadrants 1 and 3, then it's going to be more positive. Or if a general area lies in quadrants 2 and 4, it will be negative. IXY will be negative. And again, we'll say more about that later, but I'm just giving you the big picture here. And again, if an area lies exactly at the origin, in other words, it has basically an axis of symmetry or whatever, then IXY is zero because the positive and negative X or positive and negative Y terms cancel one another out, and you get IXY zero. There is a parallel axis theorem for IXY, just like we had for moments of inertia, and we will derive this parallel axis theorem. But it looks like this. So IXY, the product of inertia about a general set of X and Y axes, for a given area is equal to the product of inertia for that area about its centroid plus the area times dx dy. So it's not a single axis moving to another single axis that's parallel to it. It's a coordinate system, an x and a y axis being moved to another x and y axis where the axes are parallel and the y axes are parallel to one another. The A is the area. dx is measured from the y-axis to the y' axis. dy is measured from the x-axis to the x' axis. That should be an x' axis. And so again, if I know a centroidal IXY, and then I can move that guy to some other set of axes using this parallel axis theorem. More on that later, and we will derive it. We have table values for I bar about the centroidal axes, and some are 0, some are positive, and some are negative. Let me just pull those up. Let me see. So these are some values for product of inertia. So again, for shapes that have an axis of symmetry, the I bar is 0 for these guys. So that's easy. That's nice. However, if you have triangles, right triangles, or quarter circles, they don't have an axis of symmetry in the horizontal or vertical direction. And so they will take on a positive or negative sign depending on their orientation. Not so much their quadrant, but their orientation. And so a right triangle at this orientation will have a negative sign, and his value is 1 over 72 b squared h squared. But at this orientation, it's negative. This orientation is positive. This orientation is negative, and this is positive. Again, these are centroidal I bars. For quarter circle, their centroidal I bars are vary as well. Negative, positive, at those different orientations. And it's 0.01647 r to the fourth for these guys. So when you're applying parallel axis theorem, if all of your areas are symmetric, like the squares and circles, then the I bar terms drop out. They're just 0. But if you have a right triangle or a quarter circle, you have to figure out what its value is and what its orientation is. So again, some are 0, some are positive, some are negative. Is there an I base for product of inertia? So remember, for Ix and Iy, there were I base values of the formulas. Generally speaking, no. Ix and Iy are with respect to a single axis, so an I base formula makes sense. However, Ixy is with respect to a pair of axes, usually Ixy, but it could also be with respect to centroidal axes, I bar x prime, y prime. However, some books and tables give what I call I origin values for Ixy. So what is an I origin value? And Hibbler does this. So it's basically, so Hibbler in a script sheet for a rectangle, he gives you an Ixy for this rectangle about an x and y axes that are at the lower left corner of the square. And it's equal to 1/4 b squared h squared. So if you happen to have a rectangle resting at the origin, in other words, touching both the x and the y axis, this is its Ixy. However, what he doesn't tell you is if this same rectangle is nestled into a different corner, then the sign can actually change. And so down here, I give a formula in a different sheet, and we'll say more about this later. So if a rectangle rests in this corner, it's a positive 1/4 b squared h squared. If it's in this corner, it's a negative 1/4. If it's in this corner, it's a positive 1/4. In this corner, it's a negative 1/4. And so Hibbler doesn't tell you that. And so you have to be careful using his IXY formulas. There's a triangle and an origin where he gives you just this formula. But again, the sign can change depending on which quadrant it's in. And we'll say more about this later. And finally, a quarter circle. He gives an IXY formula, which is great for this guy that's at the origin with respect to both of those axes. But again, it's negative in quadrant 2, it's positive in quadrant 3, and it's negative in quadrant 4. So it's just be careful, and we'll say more about that later. So what kind of product of inertia problems will we work? So we're going to find IXY by integration for shapes. We're going to find IXY for composite areas using the parallel axis theorem. Once we get IXY, then we're going to use our IX values, our IY values, and our IXY values to do transformation problems. So we're going to find IX and IY and IXY at rotated axes. We're also going to find Imax and Imin and find the angles at which those guys are, if they're not at our original X and Y. We're going to use transformation equations. So this is a transformation equation. So this is I at some orientation theta is equal to Ix cosine squared theta plus Iy sine squared theta minus 2Ixy sine theta cosine theta. So in other words, if you're given an Ix, an Iy, and an Ixy for our original coordinate system, if you specify, give me a theta, like say 30 degrees, and so you say, okay, give me the I in a coordinate system rotated 30 degrees. I can plug those values into this equation, and this I here will be the I at 30 degrees. But note that I need IXY. I need the product of inertia in addition to IX and IY in order to calculate that guy. Finally, we're going to use Mohr circle. So Mohr circle is a circle. It was developed by Otto Mohr 200 years ago. And this Mohr circle is a locus of combinations. The x-axis is moment of inertia. In other words, your Ix and Iy values. And the vertical axis is product of inertia. In other words, Ixy. And so the points along this circle are combinations of Ix and Ixy at every angle of orientation of our original area. And so we're going to use Mohr circle to find Imax, Imin, and our angle theta p to our principal angles and whatever else. So those are some of the things we're going to do in the next week or two, week or week and a half. So that's the landscape. That's where we're heading. That's what product of inertia is, and those are some of the things we're going to do. It's a tricky animal. It's a complex animal. It's got some interesting properties that basically all flow from its definition, which is the integral of xy dA. But it's subtle. It's tricky. It's a strange animal. So hang in there. Try to learn this. Figure it out. And we'll talk more in future videos. Take care.